All right, silly people, here's the situation. This is the Boltzmann function here, uh, or the Boltzmann equation, I guess, and it represents the probability of finding a particle with energy state E sub n at temperature T, where T is stored in the um, inverse temperature beta, and it's also stored inside this partition function. Z is the sum on n of e to the minus beta En, right? Um, So what we're going to do first is show that the thermal average of the system's energy can be written in a certain way. Um, that the average energy, which is E bar, which is typically just the sum on n of all of the energy states, E sub n, times the probability that they occur. Um, can we write it like del beta natural log of the partition function? This is a pretty standard statistical mechanics result, actually, but we're going to prove it. So I'm going to expand this thing right here. This we don't know yet, so I'll put a question mark, because the sum on n of E sub n, but then the probability distribution is the Boltzmann equation, so it's 1 over z e to the minus beta E sub n. What we're going to prove is that the derivative with respect to beta of the natural log of the partition function equals the left-hand side of that little question mark equal sign. So just evaluating the derivative then, it's the natural log, or it's the derivative of the natural log of the sum on n of e to the minus beta E sub n. Now, the derivatives of natural logs, dx of natural logs of, I should write it in a better way, natural log of f of x tend to go like f prime of x divided by f of x. You probably learned that in Calculus 1, but gentle reminder because natural logs are weird. So we'll use that evaluating our derivative. So it's going to be negative sine, and then the partial derivative with respect to beta of the sum on n of e to the minus beta E sub n over e sum on n of e to the minus beta E sub n. You're not going to cancel out anything here. What you're going to do is you're going to notice that the denominator of this expression is just, the partition function. So we can go ahead and write that as minus the partition function on the bottom. I'll just put it here, z. But then we can actually now do the derivative that's on the top, which is another minus sign. So sum on n minus sine E sub n e to the minus beta E sub n. The minus signs cancel out, so you do get sum on n of E sub n over z e to the minus beta E sub n, which is exactly what I wrote up here. So I know the arrows are getting confusing, but for sure this is a true fact. And we just proved it. And then the next part of the problem is, for a quantum harmonic oscillator, show that the index n, show that the partition function has a specific form. And we're just going to do it. So remember the partition function was, I already forgot it. It was the sum on n of e to the minus beta E sub n. But for a simple harmonic oscillator, E sub n is just n plus a half times h bar omega. So we're going to plug that straight in, and we're going to get the sum on n of the exponent of minus beta times n plus a half h bar omega. You want to distribute the stuff inside the exponent a little bit. So you get minus beta h bar omega n minus a half beta h bar omega. Now notice that the second term inside of that exponential can be pulled outside of the sum. So we actually get something like e to the minus beta h bar omega over 2. But inside here we have the sum on n, and I'm going to write it in a funny way, of e to the minus beta h bar omega to the n. Now, I'm going to say that there is a geometric sum where the sum on n of x to the n is always just given by 1 over 1 minus x, right? That's just a math result. So the stuff on the inside of the sum now can be written, after I write this over 2 here, 1 over 1 minus e to the minus beta h bar omega. I just subbed e to the minus beta h bar omega for x, right? Which means we can certainly write it the way that old Griffiths did here, with an e to the minus beta h bar omega over 2 up top and a 1 minus e to the minus beta h bar omega on bottom. Awesome. Now we're going to use the results, this result and also the result of the first bit, to find the average energy for this guy. So the average energy again was the derivative with respect to beta of the natural log of the partition function, where this is the partition function up here. So we're going to do minus del beta natural log of e to the minus beta h bar omega over 2 over 1 minus e to the minus beta h bar omega. Instead of going straight ahead with doing the derivative, let's try to simplify the natural log a bit using the rules thereof. So it's del beta, and then I'm going to create some big braces. Natural log, whenever you have natural logs and the arguments are being divided, you can split it up as the top one minus the bottom one. So natural log e to the minus beta h bar omega over 2 minus natural log of 1 minus e to the minus beta h bar omega. Close the big braces. And then the natural log of an exponent is just the argument of the exponent. So it's del beta, big braces, minus beta h bar omega over 2 minus natural log 1 minus e to the minus beta h bar omega. Right? So let's distribute the derivative into the braces now. So we get minus braces minus h bar omega over 2 minus, and then again it's the derivative of the stuff inside the natural log with respect to beta. So that being just h bar omega e to the minus beta h bar omega divided by the stuff inside in the natural log, so 1 minus e to the minus beta h bar omega. Right? Now, because we can pull out the minus sign that is attached to each of these, so we'll get an overall plus sign. I'm also going to pull out h bar omega over 2. So we get h bar omega over 2 times 1 plus 2 e to the minus beta h bar omega over 1 minus e to the minus beta h bar omega. Let's give both of these the same denominator. So just multiplying this guy by 1 minus e to the minus beta h bar omega plus 2 e to the minus beta h bar omega all over 1 minus e to the minus beta h bar omega. This exponent and this exponent are the same, which means we can just do the subtraction and get the form that Griffiths wrote it in, which is 1 plus e to the minus beta h bar omega over 1 minus e to the minus beta h bar omega. Cool. Next, a crystal consisting of n atoms can be thought of as a collection of 3n oscillators. The heat capacity of the crystal per atom will therefore be the derivative of the average energy with respect to temperature, where this is the average energy that we just calculated, remember? So we just need to, or it's actually 3 times that quantity, but yeah. So we need to now take a derivative of this with respect to temperature. So 3 del t. We might as well move the h bar omega over 2 stuff on the other side of the derivative, since it doesn't depend on temperature of this junk. 1 minus e to the minus beta h bar omega. I'm going to use the chain rule here because the derivative with respect to t of something is equivalent to the derivative the derivative of beta with respect to t times the derivative with respect to beta of the stuff inside. I did that because the stuff inside is already in terms of beta, and I didn't want more confusion. So the derivative of beta with respect to t. Beta is defined as 1 over Boltzmann's constant times t. So obviously the derivative of that with respect to temperature is minus 1 over kBt squared. And then now we can do the derivative of the stuff inside the braces with respect to beta. It's going to be a big old fraction because we're going to use the quotient rule here. I'm just going to go ahead and put it all the way to the other side. But it's low d high, so 1 minus e to the minus beta h bar omega times the derivative of the stuff up top, so minus h bar omega e to the minus beta h bar omega, minus the derivative of the stuff on the bottom, which was just h bar omega e to the minus beta h bar omega, times the stuff up top, so 1 plus e to the minus beta h bar omega, all divided by 1 minus e to the minus beta h bar omega squared. That's pretty funky. What I'm going to do now is I'm going to move the h bar omega into these little parentheses, but then move the minus sign out. So it's h bar omega over kBt squared. And then in the big fraction, I'm going to start to distribute some terms because we're going to get, let's see, minus h bar omega plus, and that's actually multiplied by e to the minus beta h bar omega, which is plus now h bar omega e to the minus 2 beta h bar omega. Similarly over here we've got minus h bar omega e to the minus beta h bar omega minus h bar omega e to the minus 2 beta h bar omega. This term cancels out this term. That's pretty cool. And inside the square, I'm just going to change the order of the subtraction just because I can. It's totally how squaring works. It doesn't matter because the square of minus 1 is still 1 last time I checked. So I'm going to move the h bar omega from the big fraction out into the parentheses out front. I'm also going to move the minus sign out, so we'll have an overall plus sign because both of these guys have minus h bar omega on them. So it's 3 over 2, and I'm also going to multiply by kb. So in total we'll have h bar omega over kbt all squared. See what I did? So that we have just 2 e to the minus beta h bar omega, those terms add up, all over e to the minus beta h bar omega minus 1 squared. This 2 cancels out this 2, and we end up with a pretty cool expression, but we can get it even to look much more like what Griffiths wrote if we use the definition of the Einstein temperature. So theta sub E is the Einstein temperature. It's defined as being h bar omega divided by the Boltzmann constant. So that's saying that the Einstein temperature divided by temperature is equal to h bar omega over kBT, which, by the way, is beta h bar omega. So we can write both the fraction on the outside and also the arguments of the exponents in terms of the Einstein temperature divided by temperature. So we have 3 kB times the Einstein temperature divided by temperature squared, and then e to the minus Einstein temperature divided by temperature over e to the minus Einstein temperature over temperature minus 1 squared. Except I just realized that it's not exactly what Griffiths wrote, but it's probably completely equivalent, because if we factor out a, well, if we move the e to the theta e over t to the bottom, so you got e to the theta e over t down here, times, and then also factor out an e to the minus theta e over t from this to make it 1 minus e to the theta e over t squared, so this should be squared. Then cancel out the relevant stuff on the bottom. You'll get 1 minus 2, so e to the minus theta e over t times the thing e to the theta e over t minus 1 squared. So it is, in fact, moving the exponential back up, completely equivalent to what Griffiths wrote, because he had a positive e to the theta e over t up top and a e to the theta e over t minus 1 on bottom squared. My bad. I'm not going to plot it though. That's on your own.